Calculation of doses by age, body weight, and body surface area. We have 5 objectives for this chapter that we should know by the end. 1, calculate doses of medication for children and adults using body weight. 2, calculate doses of medication for children using Clark's rule. 3, calculate doses of medications for special populations based on body surface area. 4, calculate doses of medication for neonates and infants using Freed's rule. And 5, calculate doses of medication for children using Young's rule. So we have the keywords here. We should go over them in the chapter, so we won't go over them right now. Patients other than average adults may require special medication dosing. Children are not small adults, but rather a distinct population of individuals that exhibit different pharmacokinetics, medication absorption, distribution, metabolism, and excretion rate than adults. The growth and development of the child or the focus of the field of pediatrics significantly affects medication dosing. According to the FDA, pediatric stages include neonate, infant, child, and adolescent. Geriatric persons and persons with organ malfunctions also have differences in pharmacokinetics, requiring the special calculation of many drug dosages. Most individuals with renal or liver dysfunction require dose adjustments of medications, with toxic medications such as chemotherapeutics, even non-elderly adults with normal organ function may require the use of body surface area dosing, BSA dosing, based on height and weight for drug calculation. Emaciated patients, those who have excessively low body weight or muscle mass, and obese patients may also require dose adjustments for some medications. All of these groups are considered special populations because of the need for special dosing calculations. Since many dosing recommendations are standardized, average adult doses for special populations must be altered to meet the patient's needs according to age, body weight, BSA, and overall physical condition. Pediatric doses of medications may be ordered according to body weight or body mass. The most common method of calculation using grams, milligrams, or micrograms of drug per kilogram of body weight. Order therefore appears as grams, milligrams, or micrograms per kilogram. The child must be weighed with each visit to the hospital or physician's office to ensure the correct amount of medication is ordered. If weight is measured in pounds, it must be converted to kilograms. The conversion factor is 2.2 pounds to 1 kilogram. That's something that you should just make a really nice spot in your brain for and forever. All right, with that being said, let's do example 12.1.
All right, for example 12.1, what is the weight of a 22-pound infant in kilograms? So we need to look at our conversion sheet. We have 1 kilogram equals 2.2 pounds. So 1 kilogram is equal to 2.2 pounds. And we have 22 pounds. How many kilogram is that? So we have 2.2x is equal to 1 times 22, which is just 22. And then we still have our 2.2x. We want to get x alone, so we have to get rid of that 2.2 by dividing each side by 2.2. So now we just have to take our 22 pounds and divide that by 2.2, which gives us 10 kilograms. An infant weighs 18 pounds, 4 ounces. What is an infant's weight in kilograms? If a person is weighed in pounds and ounces, the ounces must be converted to pounds first. So we're going to use that conversion factor that they gave us of 1 pound is equal to 16 ounces. And we have the 4 ounces from the infant's weight. How many pounds is that? So 16x is equal to 1 times 4, which is just 4, and we have that 16x. So we want to get rid of the 16 on the side, so we only have x, so we divide it. And then we also have to divide 4 divided by 16, which gives us 0.25 pounds. So now we can add that 0.25 pounds plus the 18 pounds. So essentially the patient weighs 18.25 pounds. Now we need to convert those pounds to kilograms. So remember our conversion factor of 1 kilogram equals 2.2 pounds. And then we just simply plug in those 18.25 pounds. How many kilograms? So we do 2.2x is equal to 1 times 18.25, which is just 18.25. We want to get x alone, so we have to divide each side by that 2.2. So 18.25 divided by 2.2, which is going to give us 8.29, so 8.3 kilograms. So example 12.3, a 53-pound child has been diagnosed with epilepsy. The physician orders Dilaate and 30 milligram capsules to be given at 2.5 milligrams per kilogram per dose. How many capsules should be given per dose? So I've already wrote the conversion factor up here to do. First, we need to take care of those 53 pounds, get those to kilograms. That's our first step. So we have 2.2x is equal to 1 times 53, which is just 53. We need to divide both sides by 2.2. We get rid of the 2.2 on that side. Now we just have to do 53 divided by 2.2, which is going to give us like 24.09. So we'll say 24.1 kilograms. All right, and then the doctor wants it dosed at 2.5 milligrams per kilogram. So now we had to find out how much the patient can have based on their weight, which is 24.1 kilograms. How many milligrams can we give them? So we have 1x, which is just x, and then 2.5 times 24.1. So we get 60.25 milligrams. All right, then we have the capsules, which are just capsules. So we have 30 milligrams as 1 cap. And we need to give the patient 60.25. How many caps? Well, looking at this, so if we have a capsule that's 30 milligrams and we have to give them 60 milligrams, we're gonna just give them 2 capsules, right? If we do the math, that's what we would figure out. 30x. We would actually figure out 2 point something because we have that 0.25. We cannot give 0.25 of the capsule, so we would actually just have to round that down to 2 capsules per dose. So of course, we have our example with a 42-pound child, so 1 kilogram is equal to 2.2 pounds. And we have 42 pounds. So we can do this proportion, just like we've done for the other examples, but we can just, one little trick when it comes to the, this problem is you can just take their weight and divide it by 2.2, which is in this case, looks like 19.1. And then we can do our problem. So we have 20 milligrams for 1 kilogram for dosing. We need to give them 19.1 kilograms worth of medication. How many milligrams is that? So then we have 1x, which is just x, is equal to 20 times 19.1. So we'll do that in our calculator, 20 times 19.1, which gives us that they need 382 milligrams. We have the strength of the medication at 125 milligrams per 5 ml. We can plug in our 382 milligrams. How many ml is that? So we have 125x is equal to 382 times 5. Now we'll just do 382 times 5 first, which is 1910. All right, so now we have 125x equals 1910. We want to get rid of that 125, so we just have x on this side. So we need to divide both sides by 125. That crosses off. We just have x. And 1910 divided by 125 gives us 15.28 ml. Or we can round that up to 15.3. And we need to give this to the child every 8 hours. So we would just divide that by, to find out the dosing, so 24 divided by 8 is 3. So if we take 15 point, we'll do 15.3 and divide that by 3. We get the answer of 5.1 ml per dose.
Example 12.5, the physician orders vancomycin 10 milligrams per kilogram IV, further diluted in 100 ml of normal saline for a 46-pound child to run over 60 minutes every 6 hours. After reconstitution, the vancomycin strength is 500 milligrams per 10 ml. The full 10 milligrams per kilogram is to be given 4 times a day, every 6 hours. So use 10 milligrams per kilogram per dose in the calculation. And then our question is, how many milliliters of reconstituted vancomycin for injection should be added to 100 ml of normal saline for injection to provide 1 dose? So for that, we are going to have to first find out how many kilogram, 46 pounds. So the first thing that I'm going to do is go ahead and write the conversion factor of 2.2 pounds is equal to 1 kilogram. You can find that on your highlighted conversion sheet in the weekly study material section. All right, so then I'm going to set up a proportion. So I know that the 2.2 pounds is equal to 1 kilogram. I'm going to put that in one side of a proportion. Then on the other side, I am going to take the weight, 46 pounds, and place that directly across from the 2.2 pounds because we want to have the same units on top and bottom. And then, so I need kilograms down here. And I'm looking for how many kilograms are in 46 pounds. So this is what I'm looking for, this square here. So now I am just going to start with the X and write out my math problem. So 2.2x is equal to 1 times 46. So we know that 1 times 46 is 46. And we'll just rewrite it again so it's easier to see. Now we have 2.2x is equal to 46. We want to get the x alone. So we need to divide each side by 2.2. So when I do it over here, that crosses off. All I'm left with is the x. And then when I do it over here, I am going to take the 46 and divide that by 2.2. And that is going to give me 20.9 kilograms. The next step is going to be finding out how much medication in milligrams we're going to give the patient based on their weight of 20.9 kilograms. So we're going to take this conversion factor, which it tells us to use, and this will be our next part. So I'm going to write that out as 10 milligrams over 1 kilogram. And then on my other side of my proportion, I know I need to have milligrams on top and kilograms on the bottom. And again, I probably said this before, but if I wanted to put the kilograms on top and the milligrams on bottom, I would get the same answer. I would just have to have the same units directly across. So we're going to take our 20.9 kilogram and we're going to place that in the missing kilogram spot. And just like I said, we're looking for X milligrams per 20.9 kilograms. So we're trying to find out how many milligrams we need to give the patient based on their weight of 20.9 kilograms with the dose to be given at 10 milligram per kilogram. So we'll first start off with our X. So we have 1X, which is just X, but I'll write it as 1X for now. And then 10 times 20.9. So I'm going to get out my calculator again. And I am going to do 10 times 20.9. And that is going to give me 209. So I'm going to rewrite this with X is equal to 209 milligrams. So that's how much we need to give the patient. All right, the next thing we need to do to get the answer is to take the strength of the medication and place that on one side of a proportion, which is the 500 milligrams over 10 ml once reconstituted. So that's the strength of the medication. We need to give the patient 209 milligrams. How many ml is that? So we would do 500x is equal to 10 times 209. And All right, and then on our calculators, we would do 10 times 209, which is going to give us 2,090. And we still have our 500x. And we want to get x alone, so we need to divide each side by 500. We get x alone there. And now we need to divide that side by 500. So we're going to take our 20,090 and divide that by 500, which is going to give us 4.18 ml. So how many milliliters of reconstituted vancomycin for injection should be added to 100 ml of normal saline for injection to provide one dose? And this is going to be our final answer. Clark's rule is a method for approximating pediatric doses based on the manufacturer's recommended average adult dose by relating the child's body weight to an average adult body weight of 150 pounds. Studies have shown that the average adult now weighs more than 150 pounds. Clark's rule is being phased out as a means for calculating pediatric doses, but technicians should still be aware of the method. And you definitely want to be aware of the method for the PTCB exam. So we have the formula there, and this is also on the weekly study materials cheat sheets. The child's dose is equal to the child's weight in pounds over 150 times the adult dose. And just a little reminder, Clark's rule will never be used to determine the dose of medication with a narrow therapeutic range. That is one where there is a little difference between therapeutic and toxic levels. All right, let's do example 12.6. Example 12.6, a physician orders Cefsil for a 38-pound child with an upper respiratory infection. The adult dose for Cefsil is 500 milligrams every 24 hours. The physician did not order an amount per kilogram, so calculating the medication by the milligram per kilogram body weight method is not possible. So we're going to use Clark's method to find out how many milligrams should be given for one dose. So I have included Clark's rule up at the top. So let's just fill in our information. So I like to write CD for child's dose. And then I'm going to put the child's weight in pounds up on the top, which is 38 pounds. The, the normal adult dose is 500 milligrams. And our 150 on the bottom. And then I'm just going to take out my calculator and do 38 divided by 150 times 500, which is going to give me that the child's dose is 126.7 ml. And then it asks if the prescription is filled with Cefsil 125 milligrams per 5 ml, how many milliliters are needed per dose? So I'm going to take the strength of the medication and put that on one side of a proportion, which is 125 milligrams over 5 ml. And we know we need milligrams on top, milliliters on the bottom. We are looking for how many milliliters, so that'll be our X. And we're going to input this. Sorry, this should have been milligrams. So that's 126.7 milligrams. Now, before we do the calculation, I just want you to pay attention to how close these top two numbers are. So our answer is definitely going to be a little over 5 ml just by looking at it. So I'm going to just write out my math. So I have 125x is equal to 126.7 times 5. I'm going to get out my calculator and do the 126.7 times 5, which gives me 633.5. So rewrite 125x is equal to 633.5. I need to get the x alone, so I'm going to divide each side by 125, which just gives me x here and 125 there. So 633.5 divided by 125 is 5.068, which likely in real life we would just round down to the 5 ml, but I think that the book has like 5.07 ml. So that is our answer. Dosing based on body surface area is the most accurate method because it is based on both body weight and height. This form of calculation is often used for pediatric and geriatric patients and when dosing medications with a narrow therapeutic index, such as chemotherapeutics. BSA refers to the total body area that is exposed to the environment and is expressed in square meters. To calculate BSA in square meters, the weight and height of a person must be measured and applied to a nomogram. To use a nomogram, locate the patient's height and weight in the same measurement system on the correct lines of the chart. Figure 12.1 on the next page depicts the use of the child's nomogram for a child who is 41 inches tall and weighs 36 pounds. The intersection of the straight line on the BSA line is 0.68. So the BSA for this patient is 0.68 meters squared for a child of normal height and weight. So here is that nomogram, and you can see that line that was plotted based on that information. And that was based on normal height for their age, normal height and weight for the age, but BSA may be determined by weight alone using the additional column within the center. An adult nomogram, which we'll see on the next page, is used for adults who will fall outside of what is considered normal weight for height or those being administered medications with a narrow therapeutic index. The metric system is on the left side of both height and weight columns. In comparison, the metric system is on the left side of the height measurement column and on the right side of the weight measurement column on the child's nomogram. Pharmacy technicians rarely use a nomogram since they are typically used by a pharmacist or physician in a clinical hospital setting. It is still good to be familiar with the concept. So here is the adult nomograph calculating body surface area. A medication dose is ordered for a patient with a BSA of 1.6 at 1.5 milligrams per metered square. What is the dose? So the book is using dimensional analysis for some of the problems. So you can look at the example in the book, and if that makes more sense to you, then that's fine. But I will use ratio and proportion. So I'm going to take the 1.5 milligrams and put that over metered square, which is really 1 metered square. And then remember our BSA is in metered square. So down here is where I'm going to put that 1.6. And how many milligrams is that? So X times 1, so really just X. And then we have 1.5 times 1.6. So if we get out our calculator, we're just going to do 1.5 times 1.6, which is going to give us 2.4 milligrams. Example 12.8, a physician orders the chemotherapeutic agent cytotoxin 50 milligrams per metered square per dose IV for a 160-pound adult who is 55 inches tall. Determine the BSA by plotting 55 inches and 160 on the nomogram, and you will get a BSA of 1.75 meters square. So I know the book gives it to us on this example, but definitely practice on your own and see if you can get the same answer. And if the vial of medication is 200 milligrams for 10 ml, what is the volume of the dose? So before we can answer that, we have to do a problem with this information here to find out the cytotoxin information to be able to do that step. So I am going to take the dose of cytotoxin, the strength of it. So 50 milligrams over 1 metered square. And we have the BSA of 1.75 metered square. And how many milligrams do we need to get? So we'll do X is equal to 1 metered square. So that will just be X. And then we have 50 times 1.75. Which gives us 87.5 milligrams. Now we can figure out the next part. The medication strength is 200 milligrams over 10 ml. So we know we need to have the same units on top and on bottom. We have our answer of 87.5, and we want to find out the volume of the dose, so it's ml. So we get 200x is equal to 10 times 87.5. So 87.5 times 10 is 875. We want to get x alone. So we need to divide each side by the 200. So you get just x left on that side. Now we want to do 875 divided by 200, which is going to give us 4.375, which will round to 4.4 ml. Example 12.9, a physician orders amoxicillin TID for a 50-pound child who is 45 inches tall. Determine the BSA. BSA is 0.86 meters square. So again, the book did it for you, but you can look at the child's BSA table. The normal adult dose is amoxicillin 500 milligrams TID. Use the formula above to obtain the desired strength of the medication. So we have that formula up on top that says child's dose is equals to the child's BSA divided by 1.7 and times that by the adult dose. So I'm first going to write out my CD for child's dose. The BSA is 0.86 metered square. And I'm going to place that over 1.7. And we're going to times that by the adult dose of 500 milligrams. And we get 0.86 divided by 1.7 times 500, which gives us 252.9 milligrams. With that. All right, then we have the medication strength down here for our next question. What dose should be given if the child is going to take the 250 milligram per 5 ml? So this is kind of like that one problem where I said, just look at how close the amount that we need to get the patient is versus how much the medication gives per 5 ml. So we gotta assume our answer is going to be close to 5 ml. All right, so we're going to do 250x is equal to 252.9 times 5. So 252.9 times 5 is going to give us 1,264.5. We still have our 250x. We want to get x alone. So we're going to do 1,264.5 divided by 250, and that gives us 5.058, which will round to 5.06 ml, and the measurable amount in the real world would be 5 ml. Pediatric doses have been estimated by using Freed or Young's rules for age, which are based on the normal adult dose. These formulas will yield approximate answers and should not be used with medications that have a narrow therapeutic index. Age is no longer considered a valid criteria for determining pediatric dosing, but a technician should still be aware of the following formulas. Again, for the PTCB exam, especially. Freeze rule is used for neonates and infants up to 24 months, so the dose is equal to age in months over 150 times the adult dose. And now we can do example 12.10. Example 12.10, a physician orders amoxicillin for a 6-month-old infant. The usual adult dose is 500 milligrams. How many milligrams should the infant receive per dose? So up on top, we have the Freed's dose formula. So I am going to start out by writing the child's dose again. Well, it's actually an infant's dose, but we'll leave it at that. And the age in months. So 6 months over 150, and that's going to be times 500. We'll get out our calculator. And we'll do 6 divided by 150 times 500, which is going to give us that we need to give them 20 milligrams. If the medication is available at 50 milligram per ml, what dose would be given to the patient? All right, so I'm going to start off by writing the strength of the medication on one side of a proportion, 50 milligrams per 1 ml. And we need to give the patient 20 milligrams. How many ml is that? So I'll do my 50x is equal to 20 times 1. 20 times 1 is 20. So then we have 50x is equal to 20. We want to get x alone. So now we're going to do 20 divided by 50, which is going to give us 0.4 milliliter. Young's rule is used to calculate medications from children 1 year of age to 12 years of age. So we have the formula there. The child's dose is equal to the child's age in years divided by the child's age in years plus 12 times the adult dose. So now we can go ahead and do example 12.11. So the child's dose is equal to her age in years, so 5 years over their age in years, so 5 plus 12 times the adult dose of 500 milligrams. So if we add 12 plus 5, that's 17. So in my calculator, I'm going to do 5 divided by 17 times 500. That is going to give me 147 0.05, we'll say 0.06 milligrams. And then the next part, if the medication is available as 400 milligrams per 5 ml, what dose should we give to the child? So we'll go ahead and do 400 milligram over 5 ml. We need to give the patient 147.06 milligrams. How many ml is that? So we have 400x is equal to 5 times 147.06. So 5 times 147.06 is going to be 735.3. So 400x equals 735.3. We want to get x alone, so we're going to divide each side by 400. So divide the 735.3 by 400, and that is going to give us that x is equal to 1.84 ml.